If it will be too much of an issue, we're good. We can always watch your video. You can take your time because I know you just came back, so it will be a little bit stressful for you. We can always
Okay.
watch it. Yes.
Yeah, my computer been working all day. I've been answering emails and my computer's been working fine all day. But tonight, I don't know. I went to start the Zoom meeting and Zoom did not want to start for nothing. But I've rebooted the computer. It kind of took forever and we're getting it going. All right, so yeah, tonight, this is tonight's Zoom meeting, 9 p.m., February 22nd. Appreciate we got some participants who came out. We'll go over the assignments first for this week. We're just doing one section, 5.3. Practice problems 11 through 31 odd. Again, not for a grade. These will be covered on the quiz on Friday, due Sunday. MyLab statistics. Same spot, we're covered independence and the multiplication rule in 5.3, and then these are the problems that I picked out to work, and I believe there's 14. Just email me the percent of these 14 that you get correct. We'll have 5.4 next week, and then the test over chapter 5 will be next week. All right, let's see if we can explain what 5.3 is about. It's really not a hard section compared to 5.4. Will be much. 5.4 will be much harder, little tougher. 5.4 will be a little tougher. But 5.3 will be a little simpler. 5.3, it's called independence and the multiplication rule. Okay. If two events are independent, we'll call them A and B, then the occurrence of A has no effect on whether B will occur. This is different from mutually exclusive. Mutually exclusive A and B cannot occur together. So this is a different animal. That's what we had before from 5.2. Mutually exclusive says they cannot occur together at the same time. This says one happens, but it has no effect on whether the other will happen. Just for an example, we could correlate the number of Cokes you drink today with whether it will rain today. Do you see any connection between the number of Cokes you drink and whether it will rain today?
No.
You think you drink more Cokes, more likely it'll rain? Most people don't see any connection between these two events. Although I'll have to say, there's a lot of crazy conspiracy theories out there. Conspiracy theory is when you see the connection between two events, but no one else can see it. So yeah, there's a lot of crazy stuff out there, but we're going to stick to non-crazy stuff. Just to give you some more examples, I didn't really put these in the practice, but give you more examples. 5.3. Say number 7. Determine whether these events are independent. Speeding on the interstate, being pulled over by a police officer. I think there's a connection. The idea is, do you see a connection between these two events? Do you think if you're speeding on the interstate, you're more likely to be pulled over by a police officer? If there's a connection, then you're dependent. E, you gain weight. F, you eat fast food for dinner every night. You see a connection between those?
Yes.
Okay, so they're dependent. So you get a high score on a statistics exam, the Boston Red Sox win a baseball game. So you think you're getting a high score on your statistics test will have any effect on whether the Boston Red Sox win?
No.
Most people don't see any connection, so they call those independent. Although I have to say, there's a lot of superstitions, particularly in baseball. If somebody gets on a hot streak, I don't know if you guys know anything about baseball, but if somebody gets on a hot streak, they'll keep doing the same things, thinking it has some effect on. If a guy gets like 5 hits in a row, he'll keep wearing the same lucky socks. He may not shave. He may, there's people who take tests with lucky pencils. If they get a high score, they'll use the same pencil on the next test. You guys have any superstitions?
Mine is if you work hard, you tend to get more comfortable, live more comfortable.
Okay. All right. So here's the rub. It's a pretty simple formula. We'll do it with coins. All right, we're going to find probability of flipping 2 heads in a row. All right, we went over the sample space for this last week. Chart form. First flip, second flip. You can make 2 heads, heads then a tails, tails heads, or both tails. Okay, probability of 2 heads. You can see that as 1 outcome over 4 total events in the sample space, meaning 1/4. It's one thing that can happen out of 4 total. We'll call this method 1. Count outcomes. All right. Method 2. We're going to use formula. All right. Well, it turns out the probability of A, this is called an A and B. And again, A and the B are independent. And you just take one of them and you multiply by the other one. This is
Since we need to catch up, we're not seeing the paper.
Oh, I've got it on my screen. Can you see it now?
Not yet, Professor. It's still
Okay.
on just half the screen. Yeah.
Okay. And by the way, it does not matter how many events are in the string. So you could go probability of A and B and C and D, go forever. And it will equal all of the probabilities just multiplied. If the A, B, C, and D are independent. All right, back to the probability of two heads. Try to leave it up on the screen here. Probability two heads. We will form two slots. We want a head in the first slot and a head in the second slot. This is for a coin. All right, what's the chance of flipping a heads? 1 out of 2. So you go to the second flip, what's the chance it flips a heads? 1 out of 2. You multiply this together. I didn't mean a colon there. And you multiply, in other words, 1/4, which is exactly what we got up here. All right, if you just have two heads, both methods are probably equally easy. You can count outcomes or use the formula. But if you wanted to extend this to, say, 5 heads in a row, probably 5 heads, the formula is going to outshine the chart form. You'll have 1, 2, 3, 4, 5. Each is a heads. What's the chance of getting a heads on every flip? 1/2.
Professor, we are still not seeing it though.
Can you see it now? It's showing up on my screen. Can you see the can you see it now? Y'all are both muted, so if you're trying to talk to me, I can't hear you.
What I'm seeing now is just probability A and B equals to A bracket P, probability A bracket A, P bracket B, and then probability in bracket 2 heads equals to 1/2 times 1/2 equals to 1/4. That's what I'm thinking.
So you're seeing this. You just read me this line, right?
Yes, Professor.
So you're not seeing the line below I've just written.
No, Professor.
Wow, the Wi-Fi is really slow.
I'm seeing it now.
You seeing it now?
Yes.
Okay, on my end, it's pretty fast. There's no delay at all. On y'all's end tonight, it's really delayed.
Yeah, I'm seeing it now. It's clear.
Okay. So yeah, so this is 1/32. You probably don't see that yet either, do you?
No, I can see it now. Clearly.
Okay.
Yes.
You can kind of justify it. I won't draw out the entire chart, but on the chart, you'd have, say, heads, 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 heads. This will go on down and it will finish with tails, 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 tails. I'll let it catch up. Remember, your number of rows will be one row. All heads is one row out of 32. Well, your number of rows is 32. Your number of rows is 32, which was 2 to the 5th. So your probability is one row out of 32. I'll let it catch up. Let me know when it's catch up.
Yep. Yes, you're there. Correct.
I'm there?
Yes, Professor.
Okay. All right, well, I'll just work a few examples. Basically, in this section, all the problems are going to assume independence. And you're going to wind up multiplying a lot of these probabilities. Let me show you. Let's see. I've already done 11. Probability of 5 heads in a row. They've written out the decimal for it. Apparently 1 over 32 looks like that. We'll try 13. Page 259. About 13% of the population is left-handed. So we can translate that into a probability. The probability of being left-handed is 0.13. Let me know when you can see that. Can y'all see that?
Yes.
Okay. We're going to need its complement. We'll assume it's right-handed. We'll ignore anybody who's ambidextrous who can use both, who's both. We'll just assume the universe is left-handed and right-handed. Can you tell what that would be?
Yes, it should be 0.87.
Very good. 1 minus 0.13. It's a complement, 0.87. Can you see the 0.87?
Yes, Professor. I think it's my internet, so I switched to Wi-Fi and it's better now.
Okay, so things are a little quicker now?
Yes, it is.
Okay, very good. Okay, here's the first question. 2 people are selected. If 2 people are selected, what the probability both are left-handed? So we will, I'll just write that this way, both left-handed. Well, that would give you 2 slots. It parallels the coin with heads and tails, except it doesn't break 50-50. The percentages are 13% and 87%. But if I want them left-handed, what do you think goes in each slot?
Yes.
The 0.13.
Mm-hmm.
And what do I do with these 0.13s? Again, we're assuming they multiply. In effect, 0.13 squared. .0169. %1 chance you select 2 people and they'll both be left-handed. It's pretty small chance. All right, that's the first basic question they'll ask. Any questions about that?
I don't have any.
Okay. So then they ask an at least probability. At least. And this is a little tricky. So I'm going to write it out both ways to show you, and I'll show you I'll write it out the long way, and then we'll show you the slick way. They ask, what is the probability at least one person is right-handed? Okay, method one. Use the chart, count outcomes. All right, well, the chart, I guess I'll start with left-handed, left-handed. This exactly parallels heads and tails. Well, someone could be left-handed, right-handed. Someone could be right-handed, for the second person, left-handed. Or they can be both right-handed. Right-handed. This is person one, person two. Now, in effect, on your first question, they basically asked you to figure row one. So that is 0.13 times 0.13, 0.0169. And he just asked about row one, and so you were done. Okay, but this at least one right-handed, how many rows have at least one right-handed?
3.
The last three. So here's the long way. Probability, I'll number the rows, 3 and 4. Okay, the probability at least one right-handed will be row 2 plus row 3 plus row 4. Well, how do I figure row 2, row 3, and row 4? Well, exactly like I did row 1, except row 2 is going to be 0.13 for the left-handed and 0.87. Remember, they're independent. So you're probably getting the left-handed is 0.13, but you're probably getting a right-handed is 0.87, and they're independent. So they multiply. I could write it up here right beside it as well. Questions about that?
No, Professor. Okay.
Well, row 3 is same as row 2 in the numbers, it's just reversed. So
Yes.
row 3 is 0.87 first because it's right-handed first, and then left-handed 0.13, but that's going to give you the same number as row 2 because, it doesn't matter the order you multiply. And then you see how to do row 4? They're both right-handed. That means 0.87 times 0.87.
Yes.
So we'll multiply all that out. 0.13 times 0.87 plus 0.87 times 0.13. Could have just multiplied it by 2 and doubled it. But I'll just do it all the way out. And then plus 0.87 times 0.87. So there's all 3 rows punched. I'm getting 9831. 98% chance at least one person will be right-handed. Now, are anybody out there going, I want to do it quicker? Does anybody want to see the slick way?
Yes, please.
Oh my goodness, so polite, yes. All right, well, let's see if I can keep this on the screen, and we're about out of room. Method 2, slick way. The more technical name for Slickway is complements. Remember what a complement was? Everything else in the sample space, not in the original event.
Yes.
So you see with rows 2, 3, and 4, that's the complement to the answer for 1, to row 1. So I could very slickly get this, probably at least one right-handed by going 1 minus row 1. Well, that is 1 minus 0.13 times 0.13, 1 minus 0.0169. We are 1 minus 0.0169. There it is, 0.9831.
Oh.
Ah, yes. All right, I'll give you a hint. He's constructed a lot of these homework problems to fit this pattern. So he will ask you a beginning question, and then he'll ask you an at least question. And he intends for you to very slickly, the at least part will be a complement to what he asked you first. And you very slickly can go 1 minus whatever you figured first.
Yes.
Of course, you can always do it the long way.
No.
Do you want to see another example?
On this, I'm good.
At least you're good on this? Okay.
On compliments, yes.
All right. Well, yeah, like I say, he fits, there's a lot of parts to some of these, and he does fit this pattern on some of them. Y'all think it's pretty late, it's almost 10 o'clock, and we got going late. Y'all think you've seen enough tonight?
Yes, yes, Professor. I'm good.
Okay. How about our other participant? Miss Obey, you need to see any more? You're muted if you're trying to talk. Okay, maybe not. All right. Are we ready to end the meeting then?
Yes, Professor. If I have challenges, can I email you?
Oh, absolutely. Email me about anything, anytime.
Thank you, Professor.
Okay. Do you have anything? Your mute went off.
No, please.
No? Okay.
No.
Well, we'll do another 2
Okay.
Zooms on Thursday, 12 and 8, and hopefully my computer will work better.
Yes, please. Thank you.
Hope so. But I appreciate you coming out late on a Monday night. Really appreciate it. Hopefully we'll see you on Thursday.
Yes,
Thank you.
please.
Okay, sure thing.
Good night.
Good night.
Good night.
Good night.